Okay, shall I start?
Yeah, could you please first introduce yourself? I think you are the one who know yourself best.
Okay, hi everyone. I'm W.S. Chan. I've been at CityU for quite a few years, and today I'd like to talk about my research area, one of my research area. I'll be talking about RF microwave power amplifiers for 5G mobile. Okay, so the contents of my talk will be RF power amplifier characteristics, influence of RF power amplifiers on mobile radio signal modulation format, and in particular, the topic that I've been working on recently is the Doherty power amplifier. So I'll mention about why we have the Doherty power amplifier. Okay, we'll also look at recent works on Doherty power amplifiers, and so we'll make a start. RF power amplifier characteristics. Why is there research being done on it? In RF power amplifiers, there's a conflicting requirement between efficiency and linearity. Yeah, amplifiers at low frequency and RF frequencies have similar sort of characteristics. So, for example, if you're probably aware of audio power amplifiers, you want to have good linearity for good music. However, if you want good linearity or good signal quality, or if you're into hi-fi or audio amplifiers, you want to have a good reproduction of the music. Okay, so usually you want high linearity, but the problem is with high linearity, your efficiency goes down. Yeah, so if you want high efficiency, the linearity will go down. Okay, all right. So what's the effect of efficiency? I believe you're all aware of the effects of efficiency. If the efficiency of your power amplifiers is very bad, then your mobile phone is not going to last very long. Okay, and you see this familiar sign at the end of the day. Or if the efficiency is very low, you'll probably see it in the middle of the day. Okay, so what about the effects of linearity? If your linearity is poor, then you get interference. So, for example, there you have somebody, a husband and wife sleeping, and the husband snoring. There's a lot of noise, and it causes a lot of problems. Yeah. So these are the RF power amplifier characteristics. You want high linearity and high efficiency, but usually they're in conflict. Okay. So what are the influences of RF power amplifiers on mobile radio signal format? You probably some of you may not be old enough to have know about first generation mobile radio. So first generation mobile radio, the RF power amplifiers were mainly biased in class C because you didn't require very high linearity. Okay, so in first generation mobile radio, most signal formats were analog FM. So you can use class C, which is a high efficiency amplifier working close to saturation. Okay, so second generation, the signal format went from analog to digital, and in particular, one of the most popular ones is the GMSK, Gaussian minimum shift keying. Of course, not all second generation mobile radio use this signal format. And one of the reasons why the signal format was maintained is because you can continue using class C power amplifiers, which is has a higher efficiency, but with low linearity. But with digital FM, you could still use amplifiers that were not very linear. Okay, and as the technology for transistors began improving, in the third generation digital mobile radio, which uses, there are different formats used. For example, some use QPSK, some use wideband CDMA. You're able to use class AV power amplifiers, which were more linear and had a relatively high efficiency, not as high as class C, but relatively higher. Okay, so in fourth generation, the signal formats were also limited because of the efficiency obtainable from Class AB amplifiers. However, QAM signals, quadrilateral amplitude modulated signals, did require slightly higher efficiency depending on the level. In the fifth generation and beyond, where you use high levels of QAM and other types of modulation formats, you needed a more efficient power amplifier. Okay, the reason for that is because it's difficult because these signal modulation formats have a high peak to average power ratio, which requires operation of your amplifier below saturation. And when you operate an amplifier below saturation, the efficiency is very low. So you need a different type of power amplifier. Okay, so this is the reason why Doherty power amplifiers have become very popular. In fact, if you look at most base stations around the world, they're using Doherty power amplifiers. Okay, so modern wireless communication systems, the peak property density function of a modulated signal do not occur at saturation but at back off. Okay, so if you look at that, so what you notice is that the peak probability density function is below saturation, which means that if you had a Class AB power amplifier, the efficiency can be quite low. The ideal or theoretical shown here is about 40%, okay, which is not high. And in practice, it'll be even lower. Okay, so with a Doherty power amplifier, you notice that there is an additional efficiency peak. If you look there, look at the blue line, you notice that you can realize a higher efficiency peak at a lower power level. Okay, so that's why Doherty power amplifiers have been used in most base station transmitters. Okay, the problem is with the Doherty power amplifiers bandwidth. There are other problems. In practice, you can see that you can have a high efficiency, but in practice, the efficiency will be much lower. So there's a lot of work that can be done to improve efficiency and bandwidth. So what is the Doherty power amplifier? Well, the Doherty power amplifier is actually not very new. It was invented in 1936 to improve efficiency of radio transmitters. Okay. So in 1940, it was actually applied for a 50 kilowatt amplifier, and it was used in 35 commercial radio stations in 1940. And in 1953, there was the first 1 megawatt AM transmitter. AM, as you know, amplitude modulation requires a relatively linear amplifier. Okay, in 1980s, solid-state devices replaced tubes for low-power transmitters, and in the 2000s there was a revival in interest due to the more efficient modulation formats, in particular fifth-generation mobile radio, okay, which requires high efficiency at power levels below saturation. Okay, so here's a typical characteristic with frequency. So as you can see, the black line is at center frequency. You have a nice high efficiency at back off. As you go away from center frequency, if you look at the blue line, 20% away from center frequency, the peak efficiency drops off. Okay. I'm going to have to speed up a bit as I can see the time is running short. So here's a typical block diagram of a Doherty power amplifier. Okay, so you have the top path here, which amplifies a carrier, and a peaking path here, which amplifies a peaking signal. Okay, so the topology actually looks quite simple. Okay. And that's the sort of characteristic that you have. Sorry. Okay, so what happens is at low power level, that's this region here, the carrier amplifier turns on and the peaking amplifier turns off. Okay, so you have one one mode of operation here. At a higher power level, what you notice is that the peaking amplifier turns on, and then you have a second mode of operation. So there are different types of modes of operation, which makes the design of amplifiers actually extremely difficult. So although the topology looks simple, in practice it's a bit difficult. And we're doing a lot of research work on improving the efficiency across a wide frequency range. Yeah. Okay, so what are the power amplifier needs? The needs are high efficiency below saturation. Below saturation, it's often called output back-off. We also need multi-band or wideband. With 5th generation mobile, you notice that the frequency band has increased a lot, and there are many sub-bands. There are two frequency ranges. One is below 6 gigahertz, and the other one is in the millimeter wave. Okay, so there's a big demand for multi-band or wideband operations. So I'd like to give you some recent examples of what we've done in our team. We looked at a modified phase compensation network, which resulted in a 1.3 to 1.8 gigahertz operation. So if you look at that, it seems very simple, but requires a lot of design. So the main novelty in this amplifier is this phase compensation network. Okay, so this work was actually published quite recently. And another one is the use of a composite right-left-handed transmission line, okay, which resulted in a wider broadband range, 1.25 to 2.43 gigahertz. Okay, so again, it may look simple, but it was quite a big achievement. So here's the composite right-left-handed transmission line, and again, this work was published quite recently, last year, I believe. Okay, so these are a recent example. So the main work, research work that we're looking at is improving the efficiency and over wide bandwidth. And we've been doing work at below 6 gigahertz. So 6 gigahertz is 6,000 megahertz. And we've also been doing some work in the millimeter wave band at 28 gigahertz. Okay, so this is the research work we've been working on. That's all I have to say. Oh, I finished a bit earlier than allocated. Is there anything that I need to talk about? Okay, so anyway, okay, just some background. So I have a number of research grants to support research students. My previous PhD students, they've done quite well. One has gone to Princeton in the US. So in terms of our department in CityU, we have, as Ray Jiang mentioned, we have and we do encourage students to go overseas for a short period, whether it's within the PhD period or afterwards as postdocs. Yeah. Okay, so I'll finish there then. Can I hand it back to you, Dr. Yuan?
Yes, I think maybe Alex, we can begin your presentation. Thank you for Dr. W.S. Chen.
Okay, so yeah, if anybody are interested, do feel free to contact me via email. My contact information is in our EE website, and you can look at our details on our website or at the university website.